Hello and welcome to another one of these ADD videos. Today we're going to be discussing the concept of magnetic flux. What is magnetic flux? Well, much in the same way that we discuss electric flux, magnetic flux is just going to be the field dot the area. But conceptually what we're doing is we're trying to quantify the field lines through a closed surface. So unlike electric fields, the flux through closed surface is zero. This is due to the lack of magnetic monopoles. If you remember, we discussed this when we were talking about the electric fields. So if I have a plus charge or a minus charge, I can draw a Gaussian surface around either one of those. I can draw a Gaussian surface around this and get a flux. And I can draw a Gaussian surface around that and get a flux. Okay? But if I have a magnet, remember how magnets work, there is no such thing as a magnetic monopole. So what we have going on is all these electric field lines that are going to be coming out of the magnet would also be coming into the magnet eventually. So the Gaussian surface being closed like that would have magnetic field lines go out would also enter the Gaussian surface. So the net integral would be zero because the net magnetic field would be zero. Basically what we're dealing with is a vector perpendicular to the surface. We're going to call that dA. And then a magnetic field. And what we're going to do is we're going to look at the vectors tail to tail. So when you put them tail to tail like this, here's a magnetic field. Here's the dA segment. Theta would be the angle between the area, perpendicular area component and the magnetic field. So the formula for flux, which is phi, the symbol with the circle with a line going through it, is going to be equal to B dot dA. You've already seen, but we're going to put a little subscript of B to indicate that is a magnetic flux. And this is a dot product. And if you remember, the alternative definition for dot product involves the cosine of the angle. And the angle, again, is the angle between the magnetic field and the perpendicular area component. All right. The SI unit for flux is a Weber. And Webers, if you look at just the formula of what flux is going to be the magnetic field dot the area. Well, magnetic field's measured in Teslas and areas in meters squared. So that's basically it about magnetic flux. We're going to look at it here next in reference to Faraday's law and Lenz's law and how there's a resistance to change of magnetic flux and how systems will compensate for the change in magnetic flux by creating currents to oppose that flux, and it'll create an opposing flux as well. So that's in the next videos to come, but make sure you understand magnetic flux fully before you move on. All of this is, of course, foundational, and the key is to practice, practice, practice. I hope I've clarified things enough for you to get some problems under your belt. Check out the example videos. Thank you and have a nice day.